Hello and welcome back to a new video on my advanced networking series. In the last video we have talked about how we can communicate or at least diagnose the connection between two computers via ICMP and all the networking stuff. I mean, we don't know the parts that are in between that kind of like revolve around how the connections are routed and how the connections are secured and how we can prevent false connections that are not allowed. We haven't talked about that, but basically we have like made a connection between two systems. Now we need to also communicate data over that connection, and for communicating between two of these systems, most of the time TCP or UDP is used, and that's about it. In this video we're going to talk about TCP/IP and UDP/IP. Alright, so let's first talk about what TCP and UDP is. So both of them are transport layer protocols, so they operate on the transport layer. They also provide an end-to-end communication. As I already told you, we have the connection and now we need the communication. We have an end-to-end communication, which means that we are port-based, so we have an endpoint on one system that connects with an endpoint on another system. And by having this port-based, we can have multiple endpoints. So one system could, for example, provide a web server, a Minecraft server, a MySQL server, everything that you need within one system, and you'll be still able to communicate with each of them because each of these systems, of these applications like MySQL, HTTP, HTTPS, Minecraft, DNS, SNMP, whatever you want to have there, all of these protocols are listening to a different endpoint number. So for example, my Minecraft is 255.65 is the endpoint for Minecraft, and in this case, because it's Minecraft, it is TCP. And all of these applications basically build on top of this end-to-end communication, and this is called socket programming. So basically you can go in and with your C++ application, Windows, you can basically just tell Windows, say, hey, Windows, open up a TCP server on port 5, for example, and then if any other computer would communicate with your Windows machine on TCP5, that data would be routed to your application because you have made a server. And if you do a client, so you say, all right, Windows, I want to connect to the following server at port 5, then basically Windows makes sure that this is kind of like sent to the right, or not the right system, but at least sent out of one system with the right direction. So go to this system with that TCP port, and then it reaches some other system, and then it basically knows, all right, you have requested TCP port 5, I have a server running at TCP port 5, so I'm gonna route this request internally on my target system to that application. So basically you have two applications, one the client, one the server, and with TCP and UDP they can communicate with each other and making sure that you're actually talking to the correct endpoint and to the correct system. Let's first talk about TCP, which is the short form for Transmission Control Protocol. The two key elements of TCP is that a packet that you send is received as it was sent. This means in order and with assertion that each data is correct. So if you want to have a reliable connection, you go for TCP, and you basically, when you send something, you are sure that it is also received by the other system. It's not just send and forget, it's send and okay, done, received, or system is not reachable, error, aborted. But basically, if a communication is possible, TCP will guarantee that each packet is received as it was sent. The only issue that we have with TCP is that its control mechanisms that make this assumption, or this control mechanism that guarantees you that the data is sent as or received as you send it, these control mechanisms will slow down. Because, for example, if you send one packet and the packet is delayed on its way, we always need to wait until this one single packet is received until we can send the next one. If we cannot just say, okay, maybe I sent another packet first and no, we need to wait until it's there. And if the packet fails to be sent, or if the packet is kind of like dropped, there was an issue with the packet somehow on the way, the data got corrupted, whatever, TCP will resend it, and these control mechanisms slow this connection quite down. Some examples are for TCP are MySQL, HTTP, HTTPS, Minecraft, and many, many more. There's also a second player in the market called UDP, or User Datagram Protocol. And basically UDP doesn't care in what order packets are received and if they are even received. So UDP is basically the complete opposite thing. UDP, we just spell out packets and say, this is the data I want to send, just send it over. I don't care if it's received, when it's received, whatever, just do it. The nice thing on UDP is that it can leverage the full speed of the connection, full capacity, because we don't need any control mechanisms. We just spill our packages as fast as we can. Issue, we cannot assert that they are receiving in order. We cannot assert that they receive as sent. So in case basically there's still an error detection in UDP. So if a UDP packet gets damaged, it's still kind of like rejected from the target system, but we don't like we are not going to resend it, we're not going to know that it got dropped, we don't have all that control mechanisms. Some examples are DNS, SNMP, and various games. So by default, if you have a game, a online multiplayer game, you want to be as fast as possible to clock your servers as fast as they can to make a smooth gameplay. We don't want to have 10 FPS first-person shooters online. We want to have it desirable at 30 FPS or at least 60 FPS. We want to have a fast server that can do fast decisions, and for that each connection to that server must be fast. We don't care if a packet gets damaged on the way, because, well, if the user has a bad internet connection and thus packages are arriving late or damaged, we don't care. We do not just do it. So if the user shoots but his connection was too bad for really shooting, well, he hasn't shot. Or if a user's move event was too slow because he has a bad internet connection, he might get hit by some other people because he had a bad connection. So we kind of like need this assertion for games. Alright, so let's take TCP and UDP side by side. So first of all, TCP very reliable, while UDP is not. On the other hand, UDP is fast, while TCP is not. TCP allows ordered communication, so everything that we send will arrive in the same order. UDP doesn't not do this, it's not ordered. UDP, on the other hand, has just error detection, so there's just a checksum. So if there is an error in the packet, we're not going to allow it. On the other hand, TCP, if there is an error in the packet, we ask to resend it so we can correct the error. TCP has a receive acknowledge, so as soon as the other system receives a packet, it tells, oh, I got your packet. While UDP does not have such mechanism, we just bill packets out. And to visualize this a bit better, here is a nice animation that I have found on the NordVPN blog. It is a German article, but in case you understand German, you can go to the article and see a full description of these animations. So basically, just to recap, here we have a sender, and the sender sends the packet over the connection, and as soon as the receiver gets it, it kind of like says, check, I got it, and then the sender sends the next packet. While on the other hand, at UDP, we just spill out packages over these connections, and we don't care if they arrive, if maybe some packets get dropped. We don't care about this. We just spill out packets. Don't care. Alright, thank you for watching. We're gonna see us in the next video where we're gonna go a bit more hardware-sided. We have now had many videos of theory, and now we are basically at a point where we can understand how basic communication over the network is working. And we now can start on learning the networking hardware. This is why we are all here, because we want to have fancy and expensive hardware that we can show off to our friends and say, look, I have the $10,000 networking equipment in my home to make sure that you log in over a captive portal. Alright, so yeah, but we're going to talk about all of this stuff in the future. So thank you for watching. Make sure to like and subscribe, and have a nice day. Bye!